In the last lecture, we looked at the models for shading, but we didn't really look at implementing for anything very complex. We just looked at a cube, and a cube we could assign colors or shades to each vertex, and we were pretty okay by doing it a number of ways. But the difficulty is, what do we do if we have a more complex surface, like a curved surface or a polygonal approximation to a curved surface, so that the normals are not flat or equal over a large area, but are changing all the time. And this is the subject of what's called polygonal shading, and there are a couple of techniques that we could apply. In this lecture, we'll just talk about the basic principles, and then the next lecture we'll actually look at the shaders that implement each type of way of doing it through per vertex shading, where you color the vertices and then you let the rasterizer interpolate the colors across the fragments, or where you actually do the shading calculation for each fragment. So you start off with this basic idea that vertex colors, which we did before we talked at all about lighting and shading, become vertex shades. And so you can say, well, all we've done now to this point is add a different way of computing those vertex colors. And if we did it in the application, or we did it in the vertex shader, if we did it in the application, we would just send it to the vertex shader as a vertex attribute, as we talked about in the last lecture. Or I can, as we started to talk about, just send the parameters and then compute the same thing in the shader. Because by default, the vertex shader is going to shade by default, the vertex colors, which now are vertex shades, are interpolated across the object by the rasterizer, and so each fragment has a slightly different color if the vertices have different colors. That's known as smooth shading. If we wanted to do something as we did earlier, where each face of the cube has a constant color, we could either do it the way we did it then, by making each vertex have exactly the same color. That's a little inefficient because you're storing the same colors over and over again on the GPU and taking up space. It's much easier for each polygon to send the value over as some sort of a uniform variable that will then be picked up by the vertex shader. But that's known, regardless of how you decide to implement that, as flat shading, that each polygon has a constant color. Now, much more interested in this lecture talking about smooth shading, and there are a couple of ways to do that. So let's talk about polygon normals. We know that a triangle, is flat, and therefore it has a single normal that's the same across its whole face, so we should be able to just calculate it once. Now, if we apply the model only once, if we want to be really fast, this is what you do. This is the example that I'm going to use in a number of times here, and I'll show you some examples in the next lecture. We have that online as shaded sphere. In the notes, we talk about getting this sphere approximation by subdivision. There are lots of ways of doing it. The subdivision way is kind of nice because you can examine how many times you have to subdivide a tetrahedron to get a reasonable approximation to the sphere. The basic algorithm is like this. We take a tetrahedron where it's pretty easy to figure out 4 vertices that are equally spaced on a sphere. That's our initial tetrahedron. We then subdivide each face just as we did with our Sierpinski gasket. But the only difference now is, actually there are 2, where we don't eliminate a triangle in the middle. Every time we subdivide each face and connect the bisectors, we get 4 triangles. We keep all 4. The problem is, when I start taking the midpoint between 2 vertices to get one of those new points to determine these 4 smaller triangles, that point isn't on the unit sphere. So to get it on the unit sphere, I have to add a normalization step. So every time I take and assuming I want a unit sphere, because I can always scale that up, every time I subdivide a face into 4 smaller triangles, I push those triangles out to the unit sphere by simply normalizing those new locations. And then I can repeat that subdivision step as much as I like. So that's the model we're going to use. It's a very good one for doing comparisons. Now here's what happens if you say all I'm going to do is compute a normal for each point on here. Okay, no, excuse me, for each triangle. I compute it once and I use that same normal. Here's an easy one to see at the 3 vertices for that triangle. So I color each of the faces in a constant shade. Well, you can see this kind of is pretty bad. You could say, well, you didn't subdivide it enough times. Wait till you see the next slide. But this is what you get when you do this constant shading or on each polygon. So it's not a very good model. But suppose now what I do is do smooth shading. So what I do now is let's do it this way. This won't work in general, but it works really nicely for the sphere. Suppose I know the normals analytically. Now that may be true for some curves. For the sphere, I know that the normal of a unit sphere is equal to is the same as the vector from the origin to that point. So I know exactly what they are. And so just for testing purposes, I want to show you what happens if I use the exact normal at each vertex and I apply the modified Phong model to get a shade at each vertex and then let the rasterizer interpolate across the surface of that polygon. This is what I get. And I think this is remarkably smooth. Especially you compare it to the previous one. This is the same number of subdivisions. It's just a few subdivisions, so it's a pretty rough model. But if you look only at the interior, this is shaded pretty well. You get the only way you really know it's not very many subdivisions is this edge you observe around the corner, around the outside, which is known as a silhouette edge, because it's just the silhouette of that object, and it turns out you need an awful lot of polygons to get rid of a silhouette edge. But the point here is that smooth shading really works well. Now the problem really is this: that if I want to generalize this to a polygonal model where I don't know exactly the vertices at each point on the object, or I have to use approximations that say, okay, what I'm going to do now is compute the normal at a vertex just from vertex information, nothing about the shape of the object. That's a more realistic way of doing things. And there are 2 basic strategies that people have used in graphics for doing that. One, so here's a mesh, and Garreau proposed this quite a while ago. He said, if you look at it mathematically, here you have a polygon. It doesn't really matter here that they're quadrilaterals or any other type of polygon, but you have these polygons and they meet at corners. Now, strictly speaking, mathematically there is no normal at this vertex. Why? Because there's a discontinuity in the slope here. That all of the slope just a little bit over into this polygon is different than the slope here. So there's a discontinuity over here. Likewise, even along the edges between any 2 polygons, like here, you have a discontinuity because the slope generally is different for this polygon than it is for this polygon. But what Garreau suggested is, why don't we define a vertex normal, a vertex normal, by just averaging the normals of all of the polygons that meet at that vertex. So in this case, it happens to be 4, and what I can do is just add them together, take their sum, and then divide by the magnitude of the normal to normalize it. So the average would be these things added together over 4, but since I want to normalize it anyway for the lighting calculations, I just divide by its own. I add them up and divide by the normal of the new vector that I get. Now that's by the length of the new vector I get. So that's what Garreau shading is. It's been done for a long time. It's been built into hardware, and it fits very well with doing things on a vertex by vertex basis. So if I have a model, and the problem is I have to get this information analytically, because if I'm working a polygon at a time or a triangle at a time, the pipeline doesn't know anything about these other normals, so it can't do this. So this has to be done within the application. But as long as you have a reasonable data structure, you'll know what the vertices are for the for the polygons around the one that I'm trying to render, and so I can generally compute these vertex normals by this averaging process, or potentially even as we did with the sphere exactly. But the more important case is where you have a data structure that tells you enough information about the surrounding polygons so that you can define these vertex normals as being the average of these normals. Then you compute a shade which will now be different at all the vertices of the polygon that you're trying to render, because they're averaging together the normals from different polygons. And when you do that, you get a lot smoother rendering of the surface. Okay, now there are two methods of doing that. What Garreau said is find that average normal at each vertex and then apply the model, and then use the rasterizer to interpolate those vertex colors across each polygon. What Fong said is this is different. This is called Fong shading. I should have been a little more careful all along and saying what the model, the Fong model that we've been talking about, and the modified Fong model are lighting models. They apply independent of what you're trying to render. Fong shading, it refers specifically to trying to shade triangular meshes. So we apply the Fong model, but how we apply the Fong model where, how we get the approximations to the normals is different. So it's, be careful of the terms. Generally, we should be saying lighting most of the time, because that's what we've spent most of the time talking about. So compared to Garreau shading, Garreau said, okay, just get these, apply the model at each vertex, and then let the interpolate smoothly across them with the rasterizer. And that was fine, because that works very well with a pipeline model. Fong said, wait a minute, I can do better than that. What if I find the vertex normals? And then what I'm going to do is interpolate along the edges. So what he said is, let's do this. Let's compute a vertex normal over here by averaging. Let's compute another vertex normal over here on the left by averaging these four polygons. Let me interpolate across that using just a little linear interpolation. Do the same thing for all of these other edges. Now I can interpolate the normals inside, given what are called the edge normals, and apply the model at every point corresponding to every fragment in here. Now, there were two potential issues with doing that. One was where are you going to do it? And second, it sounds like it's a lot more work. In a shader-based world where you can program your shaders, it's really not very different. So before you could do that, when you couldn't program your shaders, people would say, oh yeah, Fong shading is much better. You would notice it. Let me talk about the comparison. If you looked at high curvatures, places where the surface that you're trying to approximate was changing very rapidly, you might notice in Fong shading where each polygon is treated sort of independently, you might see that looks Garreau shading is not going to look as good as Fong shading. And part of the reason is that it's discussed a little in the book, is that your visual system is incredibly sensitive to changes in grayscale at edges or changes in color at edges. And you get what's called a Mach band, where you see it brighter if it's going from, say, a dark shade to a white shade. You'll see it darker at the edge on the white side, and it'll smooth out, and on the dark side, it'll actually be a little brighter and then smooth itself out. And that's sort of, you're doing edge detection in the back of your eye, it turns out. So you get this, what's called these moire effects from that. So you really need to get things smooth, and Garreau shading is not as smooth as Fong shading. But as we said, it looks like Fong shading requires a lot more work, and until you were able to program the shaders, it had to be done offline, because you couldn't get that information to every fragment. Now, when every fragment is going to execute a fragment shader, now we can do this in each fragment shader, and now it becomes a lot less clear about how much more work is required. Even if it requires a little more work, you can do it pretty fast and do this. So this is called, the first case, Garreau shading is called per vertex shader, where you only apply the lighting model at vertices, and Fong shading is now known as per fragment shading. And If you're going to do this, as a last comment, is if you're going to do this for a mesh, it gets tied into what kind of a data structure do you have to represent the mesh so that you can actually get those vertex normals to start either the Fung or the Garot shading. Okay, so in the next lecture, I'm going to look at the shaders that do this, and one of the things we're going to see is that these shaders are essentially identical. It's just a matter of where we apply the calculations in the two cases.